Bismillahirrahmanirrahim and Assalamu alaikum to all of you. Guys, today I'm going to present the second part of the quick review on real analysis. So in previous part we stopped our discussion on completeness property. Now in this lecture we will continue from the concept of functions. So basically you are already familiar with the formal definition of functions. That is, for each value of the domain we have unique images in the range set, and function is denoted by y is equal to f of x. So here we are given with a function. That function whose domain is any set D and range is from the set of real number. We say our function is bounded above if there exists B belongs to the set of real number such that our f of x is less than or equal to that B for all x belongs to domain. So if this inequality holds, then we can say our function is bounded above. In that case, our this B is said to be restriction, or some B belongs to a set of real numbers. So similarly, our function f is bounded below if the set f of d is bounded below. That is, if there exists our b that belongs to the set of real numbers is less than or equal to f of x, then in that case we can say our f is bounded below. So our next key point is f is bounded if it is bounded above and bounded below. That is, there exists b belongs to set of real numbers such that f of x mod is less than or equal to b for all x belongs to that set, that is domain. You can also write it as minus b is less than or equal to f of x is less than or equal to b. So that is, here we can see our f of x is greater than or equal to any restriction, that is minus b, and our f of x is less than or equal to any restriction that belongs to the set of real number b. If this inequality hold, then we can say our f of x is bounded. So basically our next key point is a theorem which includes a boundedness of the function. So that is, assume f and g are bounded if f of x is less than g of x for all x belongs to domain, then supremum of f of d is less than the supremum of g of d, written as, you can also write it as supremum where x belongs to a domain, f of x is less than or equal to the supremum x belongs to d g of x. You can also prove it or check it with the help of example by taking the supremum of that functions. So our next key point is basically the Archimedean property. For a is equal to n of x such that n belongs to set of natural number and our x belongs to the set of positive real number, then there exists y belongs to the set of real number such that n of x is greater than y. So from this inequality you can say your Archimedean property holds if the set S is equal to 1 over n where n belongs to the set of natural number, then infimum of that set is 0. Here our S is written as open interval 0 and 1 close interval. So here 0 is our infimum as by the definition of infimum, you can remember that the infimum is the greatest lower bound. So here in that case 0 is our greatest lower bound and 1 is our lowest upper bound. So our next key point is for epsilon is greater than 0, there exists n belongs to set of positive integers such that 1 over n is less than epsilon. In that case, we consider our epsilon is very small, so that when n approaches to infinity, in that case our 1 over n approaches to 0, and 1 over n is less than epsilon, where epsilon is greater than 0. So next key point is there exists a positive real number x such that x square is equal to 2. That means x is equal to square root 2. Square root 2. So in that sense our under root 2 is real number. Under root 2 is real number. So our next topic is density of R. If x and y belongs to set of real numbers such that x is less than y, then there exists R. Here R is our any rational number such that x is less than R is less than y. Then Q is dense in R. So our Q is dense in R. You can also prove it by taking the closure of Q, that is Q closure is equal to the set of real number. Similarly, the set of irrational number is also dense in R. So now move towards the idea of Euclidean space. Euclidean space is basically denoted by Rk, and its elements are in the form of k tuples like x1, x2 and so on xk. This is an element of the Euclidean space. And similarly, we take here we are taking two elements x and y of the Euclidean space. Now there exist two properties that are inner product and norm, which makes our Rk a Euclidean space. In that case, we can say our this x is act like a vector and our y is also act like a vector in Euclidean space. If we sum these two vectors and if we multiply a vector by a scalar, it makes our Rk a vector space. Here our x and y are two vectors. This is our vector addition and this is our scalar multiplication that makes our Rk a vector space. Now at that point we are able to define our inner product on these two vectors, and that is defined by x multiplied by y. When we multiply two vectors and then we can get the inner product. This can result in summation I from 1 to k xi yi. So now norm is basically the function which is from a vector space to any field k. Basically we can find length of vector with the help of norm. So here we are defining norm as x norm is equal to the summation I from 1 to k xi square the whole power 1 over 2. So that is our norm. Basically these two properties that are inner product and our norm makes Rk a Euclidean space. Now move toward the next concept, that is interval. As you guys are already familiar with intervals that are open intervals, closed intervals, half open, half closed, and infinite intervals. So we see if S is subset of R, that contain at least 2 points that are x and y, and has the property if x and y belongs to the set S, and x is less than y, then our S is said to be interval, and it can also be written in the form of this set. Now, if we can get the sequence of that type, in that sense we can say our sequence of interval is nested. Our sequence of interval is nested. The next key point is the set of real number is not countable. So basically, sequence of real number is a function whose domain is the set of natural numbers, and the range is contained in the set of real numbers. That is a function whose domain is in the set of natural number, and range is contained in set of real number, and it is denoted by Sn. Here we have example of sequence of real number, that is 1 over n. Here our n is from the set of natural number, and in answer we will get a real number. So the terms of that sequence are real numbers. A sequence whose all terms contain in another sequence is called a subsequence, and it is denoted by S and K. So for example, 1 over 2 power n is a subsequence of 1 over 2n. Now if b belongs to the set of real number, the sequence b is equal to b, 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 and so on. All the terms of that sequence are b's. This sequence is known as a constant sequence, and this sequence is always bounded sequence. So next our sequence is Fibonacci sequence. The first two terms of sequence are 1 and 1, and we can get the other terms of that sequence with the help of this rule, that is fn plus 1 is equal to fn minus 1 plus fn, where n is greater than or equal to 2. So the first 10 terms of that sequence are 1, 1, 2, 3, 5, 8, 13, and 21. For sequence an, if our an plus 1 is greater than an, or you can say our an plus 1 minus an is greater than 0, for all n is belongs to the set of natural number, then an is increasing sequence. And similarly, if our an plus 1 is less than an, or our an plus 1 minus an is less than 0, for all n belongs to the set of natural number, then our an is said to be a decreasing sequence. A sequence is monotonic if it is either increasing or decreasing. If it either increasing or decreasing. If a is greater than 0 and an plus 1 over an is greater than 1, for all n belongs to the set of natural number, then an is monotonically increasing. Then the sequence an is monotonically increasing. Now if for our an is greater than 0 and an plus 1 over an is less than 1, for all n belongs to set of natural number, then our an is monotonically decreasing sequence. So next key point is Bernoulli's equation. This inequality is known as Bernoulli's equation for all n belongs to the set of natural number. I will also make the separate videos on proofs, so you can get the idea from them later. So the next key point is a sequence Sn of real number is said to be bounded sequence if there exists a positive real number m such that minus m is less than or equal to Sn is less than or equal to m, or you can say our Sn mod is less than m. Basically here m is our any restriction for all n is belongs to the set of natural number, then our sequence Sn is said to be bounded. Here are some examples of bounded and unbounded sequence. So the sequence minus 1 power n over n is bounded, you can check. The sequence sin nx, where n is belongs to a set of natural number, is bounded, and the sequence tan nx is unbounded. Now move towards the convergent sequence. A sequence xn is said to be convergent sequence if for epsilon is greater than 0 there exists n naught belongs to a set of natural numbers such that our xn minus x naught mod is less than epsilon for all n is greater than or equal to that number n naught. So basically in convergent sequence the distance between the term of this sequence and this fixed term x naught is less than epsilon, where our epsilon is any number that is greater than 0 but very small number. So you can also get the idea from this graph. Here our terms of sequence, I can take it as these are our terms of the sequence xn. Here I fix any number n naught, and here my term is x naught. So here I am making the epsilon strip. So here we fix n naught, and the terms of the sequence that appears after n naught will goes in that strip. So basically that's the idea of convergent sequence. It mean after fixing a number our terms of sequence are very close to some fixed term x naught. So that's basically the idea of sequence. You can also get the idea from this mod definition. So the meaning of mod is basically distance. So it means the distance of the terms of sequences and this fixed number x naught, this fixed term x naught is always less than epsilon when our n is greater than or equal to the fixed number n naught, where n naught is belongs to the set of natural numbers. So that's the idea of the convergent sequence, and the convergent sequence is always bounded. The limit of convergent sequence is unique. So next I write some proof over here. You can see. So here I will remind you about the statements of theorems, and later we will prove them. So the first statement is, let Sn is convergent sequence which converges to S, and Sn is greater than 0 for all n belongs to set of natural number, then our S must be greater than or equal to 0. And the second theorem is, let Sn and Tn be convergent sequences which converges to some limit S and T respectively. If Sn is less than or equal to Tn, then their limits I mean S is also less than or equal to T. So our next theorem is Sequence theorem. That is, if an is less than or equal to cn is less than or equal to bn for all n is greater than or equal to n naught from for some n naught, and the limit n approaches to infinity an is equal to the limit n approaches to infinity bn is equal to l, then our limit n approaches to cn is equal to l. As you can see, cn is in between an and bn. So if l is a limit of an and bn, then l is must be the limit of the sequence cn. So that's the Sequence theorem. So our next definition is a very important definition, that is the definition of Cauchy sequence. A sequence xn is said to be a Cauchy sequence if for given epsilon is greater than 0, there exists a positive integer n naught such that xn minus xm mod is less than epsilon for all n is greater than or equal to n naught. So or we can say xn minus xm mod is tend to 0 as n tends to infinity. It means the terms of the sequence get closer to each other after fixing some n naught and taking m n and that n is greater than or equal to that n naught. So you can say the terms of these two sequences get closest to each other, and the distance between them is very small, i.e. less than epsilon. So every Cauchy sequence has a convergent sequence. That is a result. Now move towards the next key point, and here is some result. If Sn is a sequence that converges to some S, then 1 over Sn converges to 1 over S. We can prove it also, and I will prove it in my coming videos, you guys can follow. So the next key point is also a definition of m-tail sequence X. So if X is equal to x1, x2 and so on, xn and so on is a sequence of real number, and if m is any natural number, then m-tail of sequence X will be it is denoted by xm and is small x m plus n such that n belongs to the set of natural number, and it can be written as x m plus 1 comma x m plus 2 and so on. Next we have a result, that is a monotone sequence of real number converges if and only if it is bounded.